Let's try problem 13.49. A sphere completely submerged in water is tethered to the bottom with a string. The tension in the string is 1/3 the weight of the sphere. What is the density of the sphere? Okay, so first things first, let's just go ahead and draw a picture. So there's my bottom, there's my sphere tethered, and there's my water above. Okay, so let's go ahead and draw the forces acting on this thing. So we're going to have tension pointing straight down, right, because the sphere is tethered to the bottom. So we got tension, and then we also have the weight of the sphere, which is also going to be down. So that's weight, but we also have the buoyant force of the sphere, right, because it's floating in the water. And that's going to point straight up, buoyant force. We'll call it F sub B. And then we also know that this thing is in static equilibrium because it's not accelerating. So the sum of all forces in the y direction is equal to 0, and it's just going to be equal to the buoyant force minus the weight minus tension. But we're also told the tension in the string is 1/3 the weight of the sphere. So this can also be interpreted as tension is equal to 1/3 the weight of the sphere. Call it W sub S. So, okay, so I was confused. And so if we just fill in 1/3 the weight of the sphere over here, we get, this becomes buoyant force minus the weight of the sphere minus 1/3 W sub S is equal to 0. Now if we solve this for the buoyant force, we get buoyant force is equal to 4/3 the weight of the sphere. Okay, so now we have it solved for the buoyant force. So the buoyant force is equal to 4/3 times the weight of the sphere. But the buoyant force is also equal to the weight of the water displaced by the sphere, right? That's what the buoyant force is. And so another way to write this buoyant force is equal to the weight of the water displaced by the sphere, or the density of the water times the volume of the sphere, right? So that's going to give me the mass of the water displaced. And then multiply it by gravity, that's the weight of the water displaced, and that's also the buoyant force. And we know that this is equal to 4/3 times the weight of the sphere. But we also know the weight of the sphere can also be written in terms of the density times the volume times the gravity. And so the weight of the sphere can also be written as the density of the sphere, which is nice because then this is what we're trying to figure out, times the volume of the sphere times gravity, right? Because density times volume is going to give me the mass, but we want weight, so we have to multiply by gravity. So let's go ahead and fill that in over here. So we got the density of water times the volume of the sphere times gravity is equal to 4/3 times the density of the sphere, right, because I'm filling in for W sub S right now, times the volume of the sphere times gravity. Now if you notice, we have a lot of cancellations here. Our gravities are going to cancel out, our volume of the sphere is going to cancel out, and we're just left with the density of the sphere, which we don't know, and the density of water, which we do know. And so let's go ahead and solve for the density of the sphere. It's going to be equal to 3/4 multiply divide through by 4/3 on both sides times the density of water. And the density of water, if you remember, should be density. It's equal to 1,000 kilograms per meter cubed. And so 3/4 of 1,000 P sub W is equal to 750 kilograms per meter cubed. And if you'll notice, this is actually less dense than water, so that's why it's floating, and that's why it needs to be tethered to the bottom. And that's problem 13.49.